Hello everyone. Today we'll be solving 785 bipartite graph. There is an undirected graph with n nodes where each node is numbered from 0 to n minus 1. You're given a 2D array graph where graph of u is an array that connects is an array of nodes that node u is adjacent to. Okay, graph of 0 okay, it's an adjacency list. Okay, there is no self edged. Graph of u does not contain u. Okay, graph of u does not contain duplicate values. If V is in graph of U, then V is in graph of U is in graph of V. Right. The graph may not be connected, meaning there are two nodes U and V such that there is no path between them. If the graph is bipartite, if there is no okay, what is a graph is bipartite if the nodes can be partitioned into two independent sets A and B. Uh, what does that mean? So that every edge on the graph connects a node in set A and a node in set B. Okay, 0, 2 and 1, 3. Okay. Hmm. So 0, 2, that connects everything in the other set. Okay, interesting question. How do I solve this? I haven't solved anything similar to this before. So constraints n is within 100. Okay, so we could perform a BFS. Uh, what we can do is, let me just, yeah. So we could perform a DFS or a BFS, I think, where let's say this is, wait, let me get this. So 0, 1, 3, 2, 0, 1, 2, 3. So let's say we start with the zeroth node, and then let's say let's associate another integer with this, which is 0. And then when we go to its children, we change the value of this, we XOR it, and then that becomes 1. So everything which is associated with 0 goes to one set, and everything which is associated to 1 goes to another set. And so if this is already, and how do we check if it's invalid? So if this is already in the other set, if this is already in 0, that means it's invalid. So let's say this case, we go from 0 to 1. Let's have set 0 and then set 1. Okay. So from 0 to 1, set 0 has 0 and then 1 has 1. And then 1 to 2, you have 2 here. But when you go from 0 to 2, you also have 2 here. So we check if 2 is already in the other one. And if it exists, we just return false directly. Okay. Right. So let's have what is this? Okay, so let me just zoom in a little. Okay, now it contains a graph with an adjacency list. So 123 02 013 3 02 013. Right. So for for a vertex in the graph, and then okay, let's call this U for U in graph, and then for where we form a DFS, right? Let's have a visit. Wait, uh, 0 is equal to that 1. Let's call it S1 and S2. Okay. We could just have a visitor that will make life simple for now. But yeah, you don't need a visited site. You can check it in the other site, but just for simplicity, I'm using another one called visited. So for U in graph, we need to perform a DFS. So wait a minute. I define DFS. Let's start with the node U. Wait, U. So, and then we also need the parity, parity P. So if, okay, now if U not and visited or add U, and then visited, sorry, uh, if P, if P, then let's add it to the first set. So S1 dot add U, and if Q, S2 dot add U. Okay, and if it's already in visited, if it's already in visited, then let's just do one thing. So if parity is 1, we're adding it to S1. If parity is 1, if parity and um, if parity is 1, okay, it's if parity is 1, we have to check if it's there in the second one. So if U in S2, then return false. Okay. So if it's not in S2, then if not, okay, else if U in S1, return false. And okay, I don't need this for now. And then, right, and then if V, it's uh, S1 dot add of U, and then D for I in for V in graph of U, we traverse it again. So DFS of uh, V and then XOR of parity. So we don't have to perform the operation multiple times. Let's call it uh, XOR P not uh, P XOR is equal to P of we XOR it with 1, right? Anything XOR 1 will give you the opposite. 0 XOR 1, yeah, anything XOR 1. So now we pass in P XOR, right? Then we do the same thing here. Okay, S2 dot add U. Then we do the same thing here. And in the end, we just return uh, let's call it res1 for V in graph. So res1 is equal to that, and then res2 is equal to that. So we return res1 and res2. I think this makes sense, right? So and then we just return DFS of uh let's say we start with the node what's the minimum length of the thing? So graph length is at least 1, so 0 comma 0. Uh, okay. First of all, this is res, and we can just uh, so we return so f not res. There is a slight problem here. Let's print out the node here and see what's going on. Okay, so 0, 1, 0, 1. Okay, got Uh, wait, test case, yeah. Okay, so we go to 1. If u in set2 return false, and then we also have to check if u not in set1 already. If 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 u not in set1, then we perform the recursion. And the same thing with set2. If we're doing it multiple times here, I think this should work now. Yep. So I think you can use either BFS or a DFS, and this is just simpler to code, I suppose. Okay, so we do have a problem here. Hmm. Returning a true, expecting a false. If there's something that's not connected to anything, if there's something that is not connected to anything, so let's say it's 1 and then 2, 3 something. What's the definition of a bipartite? The nodes can be partitioned into two independent sets that every edge in the graph connects to set A and then everything in the node to set B. Okay, so if something is empty, can't really partition this, can you? I think if something is empty, then we will return false by default. Is that a base condition? Let's try that out. If graph of view, if not graph of view, then we just return false. That is not necessarily true. I didn't take into account if the thing is if the thing is empty, but I need to see what a bipartite is. Graph may not be connected, meaning there may be two nodes, so there's no path between them. Okay, so wait, test case. Wrong answer. 03010. So 0, 1, and then 0. So it's basically 0, and then 1 is connected to 3, 2 is not connected to anything. So wait, 0, 1, 2, 3, 4. 1 is connected to 4. My bad, it's connected to 3 itself. 2 is not connected to anything, then 3 is connected to 1, and then 4 is not connected to anything. So here, right, okay, so if Yep. So if there is, if, why was this a false? So if it's empty, why was this a false? I draw this graph, that's the problem. Um, if there's an empty node, this is basically 0 to 1, and then you have 3 here. So everything in here is connected here, and everything here is connected here. A graph being empty, how does that affect affect anything here? A node having no connections. Uh, so if you have, let's say we have one connected to two, and then we have a bunch of random nodes. Doesn't really matter, does it? You can add these anywhere. I don't think this should matter. The problem is with this test case, but I don't quite understand why this is wrong. So I guess I'll have to draw the graph thing. Or should I just ask uh no, that would be cheating. I thought of drawing the graphs. So 0, 1 is connected to 2, 4, 6. So 1, 2, 4, 6. 1, 4, 8, 9. 2 is connected to 1, 4, 8, and 9. Right. Then 7, 8. 3 is connected to 7 and 8. So 7 and 3. 3 is connected to 7 and 8. Uh, 1, 2, 8, 9. 4 is connected to 1, 2, then 8, and then 9. And 5 is connected to 6 and 9. So 5 is connected to 6 and 9. 1, 5, 7, 8, 9. 6 is connected to 1, 5, 7, 8, and 9. Okay. 3, 6, 9. 7, 3, 6, and then 9. 2, 3, 4, 6, 9. So 2, 4, 3, 6, and then 9, then 2, 4, 5, 6, 7, 8. So 9 is connected to 2, 4, 5, 6, 7, and 8. Right. This makes sense. Wait, let me just give the same test case. without this? Would that still work? So why does this not work? Okay, so we have 6, 7, and 9, and then we have 6 and 9 too. So it should obviously return a false. Something's wrong with our logic. I think I figured out why. So let's say 7 is already visited and 9 is also visited. U in S2 return false. First of all, let us simplify this a little bit. So if P and U in SU then return false, and then if not P and U in S1 return false, U in S1 return false, and then let's get rid of all this nonsense. This one too. Okay, so if P two dot add guns, and then for V in graph of U, DFS of B comma E sub. Just has to be S2. If P and U in S1, What these are? Isn't that supposed to be right? Uh, okay, we're supposed to add it, right? No, yeah, we're supposed to add it. So I don't think this is right class submitted code. Yeah. So this seems fine, apart from the mistake. Okay. Yeah. So why is it returning true is the question. I did draw the graph. I think what's happening is, okay, how about this? Graph may be disconnected as well. So I can perform BFS. Wait, is this a hard problem? Thing is, the graph may be disconnected as well, right? And we need for everything. Hmm. Yeah, I think I might have missed something. What if the graph is disconnected? Then we'll have to perform a BFS on every component, right? Like a BFS or any traversal. First of all, my traversal is something wrong with it. I think so. And that's why this test case isn't working. And I'm a little bit confused. I don't think we need to find the parent of each component because we can add everything to a BFS and then so for u in graph BFS of u. not DFS of U, return false. If and more, U in S1. Unquestionable type list. Class list for U in graph DFS of U. Okay, okay, my bad. It's not for. I think of the perform. My bad. I have to perform the vertex and range of the length of the graph. N is equal to length of the graph. Length of the graph for vertex and range and then we perform. Okay, there is. Okay. If if it's not already there, we only have to perform the DFS if it's not already in one of the graphs, right? So if we not in S1 or we not in S2, then we perform the uh, wait, yeah, if DSM, if not, sorry. Okay, so let us. The result is false. S1, S2, and then 0. Okay, it should be and, right? My bad. Okay, now it seems fine. I forgot I used an or instead of none. So if not DFS of that, then we return false. and that seems fine. Um, false. I don't know if this is the cleanest way to write it, but yeah, that should solve the problem. So basically, what we're doing is we start with the first node. Let's say we have 0, 1, 2, 3 nodes, and they're connected somehow. We don't know that. So we start with the first node, and then even if it's disconnected, let's say 1 and 2 are connected like this, and 2 and 3 are connected somewhere here. So this part of the graph will we check if it's bipartite. And if we have n components in a graph, if each component is bipartite, that means the whole graph is bipartite. So that's what I'm doing. Initially, I was only checking one component, and the other one I was just I didn't even consider it. So I thought the graph was connected. So if it's disconnected, I didn't uh, perform DFS on the other nodes. So this is what I had to do. Thank you for watching.